Hello, good morning, good afternoon, and good evening. Thank you very much for coming to this webinar presented by Park Systems in support of nanoscience, nanocharacterization, and nanometrology technologies and knowledge sharing all across the globe. My name is Gerald Pasquale. I'm with marketing with Park Systems, based here in Santa Clara in the United States. And today we are finally restarting a webinar series, or rather our webinar efforts here in Park Systems in earnest. And we're doing so with the launch of a new series with a very familiar speaker. I have today here Professor Rigoberto Advincula of the Department of Macromolecular Science and Engineering over at Case Western Reserve University. And today we're going to be debuting a 101 type series, a series dedicated to being beginner-friendly and introducing the basics, fundamentals of engineering and research efforts in various material science fields. Today, obviously, you've signed up for the ceramics webinar. And before we get started, since it has been a couple months since we've regularly had webinar sessions, I'd like to go over a few house rules. You'll notice that your microphones are turned off by default, and that's by design. We will be having Q&A. We will be doing that in a dedicated session at the end of the professor's talk. So instead of verbally asking your questions, what we are asking attendees to do is go ahead and use the chat module or the questions module in the control panel, that little window that opened up on your screen when you joined the session. Use that to type in your questions. And what we'll do is at the end of the talk, so sometime within this next hour, we will answer those questions sequentially with the professor. All right, I think with that out of the way, that's really the only big house rule. I'm going to go ahead and turn things on over to Professor Advincula, and we will get started with the session in earnest. All right, Professor, I've turned over presentation rights to you. How has your day been so far?
Oh, very good, Gerald, and thank you for reintroducing our webinar series. As Gerald mentioned, we are focusing on what we call the basics or 101 series. And of course, that will not limit us the opportunity to talk about other more advanced topics or more popular topics, but certainly what we would like to do is in a 30-minute time frame, allow one to capture the some of the essence of the materials topic that we're going to cover and leave enough room for the audience to ask questions. And actually, a lot of these webinars are archived with Park AFM systems as well as YouTube. And of course, you'll have the opportunity to view them once this has been made. So with that, I'd like to start the talk. I'm going to talk today about ceramics and glasses 101. And this is an introduction as well as an overview of the area of ceramics and glasses, a very important branch of material science, very relevant to things like superconductors or uses even in the oil and gas industry, sensors, different types of solid-state devices, and so on. So like before, I would like to introduce where I'm affiliated with Case Western Reserve University in Cleveland, Ohio. We are a comprehensive research university with many departments and institutes, notably even the medical campus. We're located next to Cleveland Clinic, but also lots of cultural opportunities within the university circle. This is my building. We're located at the 5th floor. These are our crew members. We do a lot of research related to coatings, 3D printing materials, different types of polymer and nanomaterials as well. Secondly, we are part of a growing community here centered on 3D printing and additive manufacturing, including the ThinkBox Center or Institute, where we have access to a lot of 3D printing, additive manufacturing facilities, not only open to professors, but especially to undergraduate students who are very eager to first produce their prototype and try different materials and methods for 3D printing, even on the entrepreneurial side. So let's go on formally with materials and ceramics. This chart outlines the three basic classes of materials. One would be metals and alloys. Second would be polymers and polymer engineering materials. And then third, ceramics. So more or less you can bucket different types of materials that you encounter in these three main classes. Now, with ceramics, there are several applications and terms that you may be familiar. One is called refractory. Sensors used as dielectric for capacitors, magnetic recording, even in your credit card. Of course, insulation, space shuttle protection for very high temperature, formulation of paints and coatings, of course, what we naturally have in our bone and teeth, and automotive in terms of spark plugs. Now, if you look at all these applications, then you will see that as a major class of material, they have industrial, medical, as well as different types of solid-state device application. Now, I like this chart because it summarizes somewhat the properties, including thermomechanical properties of these three types of materials, and helps you identify where ceramics shine. For example, between metal and polymer, ceramics are the hardest materials, or the very high hardness. The elastic or bulk modulus is high for ceramics, as well as metals, but weaker for polymers, unless you use high-performance polymers. Ceramics have high temperature strength, whereas metals and polymers, of course, would melt. However, the thermal expansion is very poor for ceramic, but very good for metals and polymers. The ceramic is also poorly ductile, whereas a polymer and polymer can be bent or reshaped. Ceramics have very high corrosion resistance, whereas, of course, you have very poor properties with metals, as well as polymers because of the diffusion properties may not have as high resistance when used as a coating. Ceramics have very high abrasion resistance or resistance to wear compared to metals and polymers. Electrical conductivity, you can sort of tune it based on their dielectric properties. Certainly metals are number one. Density, you can have very porous ceramic materials. And even compared to polymer, you can have light weighting. However, metals have the highest density among the classes. Certainly, thermal conductivity can be tuned as well with ceramics, high in metal but poor with polymers. So why and what are ceramic materials? Ceramic materials are classified as inorganic, non-metallic materials and things made from them. So it's a non-metallic, inorganic, meaning it can be mineral-based or it can be synthetic-based. They may be crystalline or partly crystalline. They are usually formed by the action of heat and subsequent cooling. Most ceramics are compounds and alloys between metals and metallic elements. And either they are totally or predominantly ionic, but may have some covalent character. We're talking here about the chemical bonding properties. Clay is probably one of the easiest to identify as an ancient ceramic material, and it is heavily used, of course, as additives, but also for making domestic and industrial and building uses such as clay pots, clay bricks, and so on. A wide range of materials that includes clay, sand, and feldspar are mined, extracted, and used in a lot of construction industries. In fact, the term ceramic comes from the Greek word which means burnt staff or drinking vessel. indicating that the materials are usually achieved with a high degree of heat treatment in order to get the desirable properties. So you need to bake them or heat them at a high temperature in order to get the properties of a ceramic. Now, ceramics, there are several classifications. Can be looked at as refractory materials, abrasives, glasses, and a class of advanced ceramics that are used with low volume but high performance or high cost. Ceramic materials, for example, if we classify it this way in terms of some uses and everyday things. So, for example, glasses have their optical, packaging, composite uses. Clay products are, of course, for pottery or different construction materials. Refractories are typically what lines up ovens or different types of steel furnaces or things that end up, for example, with the space shuttle. In other words, they are used for processing at high temperatures because of their high insulation and ability to shield heat transfer. Abrasive materials would indicate that of higher wear and tear function. So, for example, what you'd find in a cutting, polishing tool, sandpaper would be granular ceramic materials. Cements, of course, will be made up of different types of mined materials. They are used as structural composites, industrials. And then, of course, advanced ceramics would be used for engine parts, rotors, valves, bearings, sensors, and so forth. So hopefully we'll get some examples of each of these uses by the end of the talk. So what are the general properties? Again, ceramics have high hardness and therefore can be quite brittle. They can withstand a lot of compression. They're very chemically stable, typically have very high melting temperatures, but some of their properties are poor in terms of electrical and thermal conductivity, although this can be tuned as well. Here are examples of several raw materials based on their classification as oxide or non-oxide based materials. So oxide materials, of course, will be the simplest to look at as metal oxides or metal oxide alumina or other types of transition metal oxide materials. On the other hand, the nitrides, the silicon nitrides, the silicon carbide are a class of itself, and these are non-oxide materials. So what characterizes these materials are that they have a high bulk or elastic modulus component, high melting point, limited electrical and thermal conductivity, low thermal shock resistance, stability at high temperatures, and of course, chemical stability. So the form factor of these materials make them competitive with metals and polymers in many applications, or simply these are the only materials that can do the job, especially with high temperature and high insulation properties because of their poor electrical and thermal conductivities. So furthermore, what are the classes that we're looking at? When we're looking at nitride ceramics, this will include your silicon nitride, aluminum nitride. When we're looking at the oxide ceramics, predominantly aluminum, magnesium, zirconium oxide. And then we're looking at silicate ceramics, porcelain, magnesium silicates, clay. But we have the non-oxide equivalents, which would include your carbides, nitrides, and a lot of them are actually advanced ceramics or used for very, very high-end applications. We will have a separate overview on glasses, and glasses are, of course, mostly silicates plus additives that allow you to control their composition as well as processability. Traditional ceramics, if you're curious, would be your pottery, your compact ceramics, porcelain, earthway, bricks, refractory ceramics. These are usually mineral raw materials or mined, and that will include sand, clay, feldspar, etc. Clay by itself has many branches or many classifications based on the aluminosilicate composition. And then what we call advanced ceramics or engineering ceramics will indicate that they need to be cured, crystallized, they need to be processed very specifically for high-end performance, whether it's refractory application or piezoelectric, ferroelectric, barium or strontium titanate, lithium niobate for electro-optics, nonlinear optics, abrasive ceramics like silicon nitride, silicon carbide, molecular membranes, or even superconductivity materials such as ytterbium, barium, copper oxide, or even barium, various types of biomaterials or bioglasses, or even biocompatible surfaces made up of hydroxyapatite, or very useful for bone growth, like calcium hydroxyapatite materials. So here you can see the wide range of classes, again, classifying them as oxides or non-oxide type of ceramics. So within the oxide family, and I will not go deep into the lattice and super lattice arrangements of these metal oxide compositions. Basically, the crystallinity of the ceramics are very important because it allows you to control their eventual thermomechanical properties as well as limit their thermal and electrical conductivity tunability. So for example, the glass formers are typically your silicate and boron oxide type of lattices. You can modify glass through different sodium, potassium, and magnesium or transition metal oxides. And then the aluminum oxides, which have a tetrahedral arrangement, and you can basically dope it with different types of aluminum silicate composition. Can be used to modify glass and aluminosilicate properties as well. How do we form them, or industrially, how are ceramics processed? Well, other than the mineral materials that are derived from clay, the ground, or mine, if we have a powder that represents different types of oxide and non-oxide compositions, they are usually best processed initially as powders or particles that can be created into shapes or hold into shapes by a binder material and then heated to high temperatures. The heat treatment gives it its final product properties, and then finally the form factor or the shape determines the application. So a lot of this alloying or composition is basically made on the powder itself. Once it sets, there's very little you can do to change the shape, or there's very little that you can do to change some of its properties in that it's in a way, I don't want to use the term thermoset, but basically because of the strong ionic bonding character, they are insoluble, they are intractable, and very highly abrasive resistant. So a lot of this is basically very strong ionic bonding properties among the metal oxide and non-oxide compositions. Here, this chart might be useful. Several ways that they tend to strengthen ceramic properties. This could be addressing the brittleness of the material because of the high crystallinity, or designing components that minimize residual stresses, or based on tensile strength control. And a lot of this is actually done by the composition as well, and also during the heat treatment. So unlike metals, in which you can have domain and grain boundaries that can be controlled based on the annealing methods, here you basically have fusion properties. And a lot of the high temperature curing, which I will not have time to cover here, occurs at very high temperatures. Sintering, that might be a term that you can use, which at that point, most metals and of course all polymers would have degraded already. So let's look at some of the classifications and application of these materials. As I mentioned early at the beginning of the talk, we will try to limit each of these tutorials to 30 minutes and perhaps leave room for more questions. So I would not be able to cover a lot of the different applications, especially with solid state devices, different types of processing methods. But hopefully I'll cover enough to pique your curiosity and go to some of the state-of-the-art application. So let's focus first on refractory materials. Refractory means it retains its strength at high temperatures, say greater than 500 degrees C. It must be chemically and physically stable at high temperatures, need to be resistant for thermal shock, should be chemically inert, and have specific ranges of thermal conductivity and thermal expansion. That is why a very common use of refractory ceramic materials are linings for furnaces, kilns, incinerators, crucibles, reactors. If you go to the lab and look for your high temperature oven or crucibles or different types of high temperature reactors that can go beyond 1000 degrees C, you will see linings of ceramics on the side of those ovens or vessels made up of this high temperature resistant or poorly temperature conducting refractory materials. So this would include compositions based on aluminum oxide, silicon oxide, calcium oxide, okay, fire clays, etc. Zirconia is sometimes used for extremely high temperatures. Silicon carbide and carbon are also used for very severe temperature conditions, but the problem is it cannot resist any oxygen in their environment. Otherwise, they easily oxidize and, of course, combust or burn. So for refractory materials, they can be produced in high volume, large furnaces such as you find in the steel industry, or small cabinets where you can basically graphitize, digest, or heat up and remove any organic components. So basically, beyond 500 degrees C, 750 degrees C, most organics are gone. Metals start melting. But once you go to 1,000, 1,500, 1,800 degrees C, you'll only be left with ceramic or refractory materials. Now, what is the composition of some of these refractory materials? So as you can see here, fire clay would be your aluminum oxide, silicon oxide, magnesium oxide, silica, predominantly siliceous material, some calcium oxide, and you can see these refractory materials having a degree of porosity. Now, that degree of porosity is actually quite important because the ability to transfer heat or to allow heat to be absorbed through the ceramic materials means that temperature will have a very high conductivity with basically either air or vacuum. So that degree of porosity is quite important for the selection of different refractory materials. Now, let's talk about advanced ceramics. So advanced ceramics, technical ceramics, engineering ceramics, are high-end, highly specialized applications. They would have unique mechanical, electrical, abrasive properties, even biochemical properties, and therefore has to be processed properly. In fact, it's very important to have structure, composition, and property relationship among these materials and the way they are processed in order to make them very useful for the intended application. So some examples, of course, of high-performance oxide ceramics would be aluminum oxide, zirconium oxide, aluminum titanate, to name a few. High-performance non-oxide ceramics would include silicon carbide, silicon nitrides, aluminum nitrides, and others. And then, of course, we have composite materials made of a metal matrix composite or a ceramic matrix composite. And you will find a lot of this in terms of what is used by the automotive industries, the electronics, solid-state display devices, even in medical technology, tooling industry, and other academic research. So for example, medical technology, with the aging population, you'll see a lot of implants being done with hip replacement, bone replacement, maxillofacial surgery. So titanium alloys are very important for this application. Or different types of abrasion-resistant surfaces, like the carbides and the nitrides, are used for wear and tear and are highly valued in tooling and other mechanical parts. Things like oxides are used in car engines, or different types of silicate ceramic materials are useful for applications not only for insulation but thermomechanical wear. So these are advanced ceramics, highly valued in the industry. They are for the size and the price, their high performance cost ratio makes them unique, and probably the only thing that does its job. So for example, let's look at the car industry. What type of applications for advanced ceramics are there? Well, you have things that are operating at high temperatures with high efficiencies against friction losses, cooling system, the requirement to decrease weight in engines means that ceramics are going to become valuable as metal replacement. However, one needs to again pay attention to disadvantages. Unlike metals that are ductile or polymers that are more processable under viscosified medium, ceramics are not. Ceramics are brittle materials. Their void spaces or internal voids are very hard to remove or can be controlled by looking at ways to change density. In other words, ceramic parts are more difficult to form and even machine. Yet these materials, when properly made, are the only materials that can do the job compared to your metal and polymer materials. So automotive industry will increase its usage, especially for under the hood applications for ceramic materials in the future. Abrasive ceramics are very much used for cutting, grinding, sanding, different types of particle processing. Common abrasive materials will be your aluminum oxide, your silica, sand, silicon, tungsten carbide, etc. A lot of this have found its industrial uses, even in do-it-yourself type of applications that you can get from Home Depot. But for wear and tear, ceramics are very reliable compared to many other applications. So for sure, whenever you have an abrasive application, cutting, grinding tools, you have a lot of ceramic components. Let's talk about high temperature superconductors. So probably you've heard for this in decades that superconductivity is basically a phenomena where you have zero electrical resistance and expulsion of magnetic fields when cooled below a critical temperature. So interestingly, the high temperature superconductor is almost a misnomer because the superconductivity is achieved at temperatures below, let's say, the boiling point of most gases. But there is a quest to get a high temperature superconductor so that it can become more useful industrially. So for example, in the column, what you'll see is the scale given in temperature in terms of their superconductivity for various materials in Kelvin. So mercury, niobium, other alloys are considered low temperature superconductivity materials. However, copper oxide superconductors are known to be of the high temperature superconductivity application. So if you are successful, or one is successful in utilizing these superconductivity properties, then they can find utility in different devices, capacitors, electrical grid, okay, magnetic levitation, for transport, etc. Here you can see the quest towards the increasing temperature of critical temperature of various materials and crystalline structures. Again, a very interesting area and their corresponding temperatures of the gases. So liquid helium, liquid hydrogen are given in kelvins, liquid nitrogen. So certainly liquid nitrogen and above would be of high interest for real world applications. Let's talk briefly about glasses. So glasses, most of what we associate with them are for applications such as windows, bottles, drinking, glasses, pipetting. But a lot of glasses, of course, are optical. So their ability to absorb, transmit, reflect light is very important for many applications. They are, of course, produced through fusion temperatures. Basic material would be sand, but sand itself has many ingredients, including sodium carbonate, soda ash, so that when you fuse all of these ingredients at the temperature about 800 degrees C, you'll get your typical glass, or even an ancient way of making glass. Now, other chemicals that will be found in glasses would include your calcium, magnesia, or calcium oxide, magnesium oxide components, including limestone, dolomite. These are the mineral names for calcium carbonate and magnesium carbonate. So glasses can be classified in terms of their properties as well as processing method. Flat glass, float glass, tempered glass, annealed glass, laminated glass, okay? Glasses that are used for optics, laboratory equipment, Pyrex, quote unquote, thermal insulators, reinforcement fibers. In fact, a lot of glass is actually used for making glass fiber reinforced polymer materials. So think about boats, think about panels, structural transport made up of fiberglass type of materials or composites. So what is glass made of? Glass is depending on the composition or type, could be fused silica, borosilicate, fiberglass, okay, glass ceramic. So you can see here various compositions of silicon oxide, sodium oxide, calcium oxide, aluminum oxide, and a very important component based on boron oxide compositions or borosilicates, for example, with a very high composition of boron oxide. Key properties of glass. These are again brittle materials, relatively high mechanical strength, low coefficient of thermal expansion, relatively high temperature capabilities, good dielectric properties, good biological compatibility, or even chemical inertness, thermal shock resistance. Now, one thing that differentiates glass from ceramics is that glass is actually melt processable. You can have a glass transition temperature, a temperature by which as you heat the glass towards melting temperature, you're actually able to bend it, or it exhibits flexural strength or flow properties such that you can even 3D print glass. And unlike your ceramics, which has to be heat cured or makes use of a precursor material, glass can be processed directly in the melt. And again, here are some of the properties of glass. They are brittle materials, therefore very high elastic modulus as a function of composition. um, low low mechanical strength. Okay, they're generally insulators, but you can modify some of these properties with different types of conducting additives. Okay, they are able to absorb different types of thermal shock. So it's very common that you have high thermal shock resistance on glass and glass ceramics. In other words, they will not easily break or shatter with certain degree of thermal conductivity. And of course, let's talk about composites. So composites are when you utilize ceramic, even glass fibers as filler materials for preparation of, let's say, textile or automotive body panels or fiberglass reinforced containers or boats. So in a world where everyday things are actually dominated by polymer materials, how can we improve the property of polymer materials such that they will have properties closer to metal or other types of materials that properties that can withstand abrasion or heat or light weighting. You know, think about replacing metals that are used in aircraft. So carbon fiber or glass fiber or other types of silicate, aluminum silicate composites. So this is what we're talking about when we mention composites. So ceramics and glass materials are basically grounded into particles, which you can disperse, and that particle can produce more density on a material or prevent stress crack propagation. Ceramics and glasses can be made into fibers or high aspect ratio particles, which can be aligned or mixed to produce random or aligned orientation. Structural, meaning you have different types of fibers that are lined up, wounded, or produced as surfaces which can then be immersed or impregnated with the, let's say, a thermosetting medium such as epoxy. The last topic that I want to touch on is 3D printing. Can we 3D print ceramics and glasses? Of course. The precursor material could be as easy as a clay dispersion, which has a thixotropic property, can be 3D printed with a printing head that moves from a digital file or a program to reproduce the shape, size of the material you want. So for example, in a viscous solution printing method, you can 3D print, let's say, this clay composition or any other type of composition with the resolution being dependent on the type of printing device you have. Once you form these shapes, they're not actually useful yet as a ceramic. You have to take them and you have to cure them. That is, you have to use heat treatment like any other ceramic material in order to get their refractory, insulating, abrasive property, and of course, as shown in very interesting shapes. So yes, 3D printing of ceramics is a whole new ball game to produce different types of form factors which can take a digital design, and some of them can be interesting bio-inspired designs that can be 3D printed and then put into the oven, and then finally you can have your ceramic printed object. 3D printing glass, yes, you can. So basically the advantage of glass is you can melt flow it. Once it's in a melt flow condition, you basically at a high temperature produce the object or the pattern based on the movement of the head, And as you can see here, it's as much as art as perhaps structural, but certainly a fascinating way of looking at glasses and ability to create new objects and functions based on 3D printing. So that's it. As I said, I'll try to keep these tutorials to within half an hour and leave more room for our audience to ask questions. So with that, thank you, and I'll be happy to answer any questions.
All right, thank you very much, Professor. So as we wait for some questions to enter the queue here, I'd like to remind everyone the mics are disabled by default. Go ahead and use the chat or questions module in your control panel to type them in, and we'll be answering them sequentially. Anyway, I'd like to put in an aside here. It's actually an interesting coincidence that you had mentioned 3D printing here, Professor, for ceramics and glasses, because just, I want to say 1 or 2 weeks ago, I'd actually been messing around with a MakerBot replicator. I forget exactly what model that we were using, but we were putting an ABS and PVC filament in there. And I was actually trying to make a gift of a 3D printed camera to someone, non-functional, even as a pinhole. But I was thinking, wow, I wonder if we'll ever get to the point where I can try and make this out of something a little bit tougher like glass. So just a question for me then, Professor. I know that PVS or plastic-based 3D printing solutions are out there for consumer level. How far are we away from seeing ceramics and glass go to a more consumer-grade end product rather than industrial?
Mm-hmm. Yeah, ceramics, certainly a lot of people have been working on it for a while. Glasses, more recent, simply because of the temperature requirements to melt and then melt flow process these materials. So ceramics can be made at room temperature in terms of the printing itself. All you need to do or end up is have a viscous thixotropic media that can be printed, as simple as a syringe, really moving that syringe head to the digital design or file or slice of that object. And then to get the ceramic property, then that's when you need to heat it up at a high temperature in order to fuse it and end up with the object. And of course, like any ceramic, they can be brittle. You drop it, you have properties that can be improved by glazing. In fact, if you want to make your own ceramic cup, you can do that, although you need to do some glazing in order to get a aesthetically and functional mug for your coffee. But certainly, like any media, it also has limitations. So the 3D printing itself, you're limited somewhat to the resolution. Unlike your traditional 3D printing with SLA or SLS or FDM, where you have a finer resolution with head. Ceramics does not have that fine resolution yet. So I would say that would limit some of its industrial applications.
Good point. Yeah, I haven't actually thought about the fact that with alternative media, you could print down to a finer resolution, have finer details in the end product, whereas if you're working with something like ceramics or glass, that might not necessarily be the case. So you would have to have, I guess, larger scale models of what you had intended to print in the first place. Okay, so I guess we'll give maybe 1, maybe 2 more minutes for people to go ahead and type in questions. So far, nothing's come in. With that in mind, Professor, do you have any closing thoughts on this topic of ceramics that we went over today?
Well, certainly as we start this new series, Gerald, my hope is to equip some of the basic concepts, classification, definition, application of materials, different materials, methods of materials, analytical methods for materials that can be useful for the novice or the student who's just trying to get into this or maybe supplement things they read on the text. Certainly, as we embark on this series, I would like this to be as much benefit to the wider audience who will purview or review this presentation materials. Incidentally, I would like to mention I am the new editor-in-chief of the MRS Communications Journal, Materials Research Society Communications Journal. And for those of you who are looking for places to publish your best work, I do invite you to consider MRS Communications as a platform for broadcasting your work to the community.
That's right. I actually just saw the press release go around yesterday on you succeeding, I believe, Peter Green over there at MRS Communications. So congratulations, Professor.
Thank you. Yeah.
All right. Well, it looks like we have no questions at this time. However, I'd like to make our contact information again available to everyone who is either coming up with questions after the fact, after today's session ends, or if you're watching this on the recording, that will ultimately be up on YouTube. So the professor can be reached again at Case Western Reserve University. His email address is at the bottom of the title slide, currently displayed here, rca41@case.edu. If you have any questions at all for Park Systems or any of the nanocharacterization techniques that we offer to examine materials such as ceramics, such as glasses, we can be reached at parkafm.com or inquiry@parkafm.com via email. You know, interestingly enough, for members of the audience here, we have a complimentary, we just happen to have a complimentary webinar later this month that might be of use for those of you interested in ceramics nanocharacterization. A member of our application staff, Dr. Christina Newcomb, she will be presenting a webinar much like this on piezo electric force microscopy, or piezo response force microscopy. And I believe the sample that she has in question for her talk are multi-layered ceramic capacitors. So she's looking at ceramics that are being used in electronics. So the information for that particular session will be going out maybe towards the, I want to say the end of next week, but that will be another webinar that we'll be giving here from Park Systems, and it just happens to tie in neatly with the 101 series here that we launched with Professor Advincula today. So keep an eye out on parkafm.com, keep an eye out in your email inboxes, and also at youtube.com/user/parknano. It's kind of a mouthful, but if you search for Park Systems on YouTube, all of our webinars, all of the recordings have been recut and uploaded for posterity there, and you can go ahead and share those with your colleagues, your students, and anyone else who might be interested in all the different fields that Professor Advincula and our other speakers have been giving throughout the past couple of years online. On behalf of everyone here from Park Systems, as well as Professor Advincula, we thank you very much for taking time out of your busy day today. And that'll be the end of today's session. Thank you very much, and have a good day, everyone.